Hey guys, what's up? Kelvin here. So, the video that you're about to watch has been filmed about a month ago now. I just got around to editing it. Sorry I haven't uploaded. It's gonna be chalked up to me being busy and having a lot of other stuff to do, being involved in commuting in a lot of other ways. So, I haven't really had time to dedicate myself to filming and editing and all of the other things that go along with making a YouTube video. But I am back for now. I will hopefully be finishing up the Unified MPLS series soon. I know that I do have a lot coming up, so that might not be as timely as I say it is, but hopefully I can get around to finishing the Unified MPLS series off so that I have a complete series on the YouTube channel covering Unified MPLS. So the video you're about to watch, again, which has been filmed over a month ago, covers the architecture and the overview of Unified MPLS, but I'll let past me from a month ago tell you more about that. See you guys later. Hey guys, what's up? Kelvin here. So, today we're going to be discussing Unified MPLS. So, I'm going to be introducing the Unified MPLS architecture to you and discussing some of the operational details and theory behind how Unified MPLS actually works. So, if that sounds fun to you, then I hope to see you after this intro. See you on the other side. So what I want to do just real quickly right now is just outline what we're going to do in this video. So the first thing that we're going to do is highlight some of the hallmark features of the Unified MPLS architecture. Just to introduce you to some parts of the Unified MPLS architecture, you can see I've got a topology diagram pulled up here that we're going to go ahead and take a look at and analyze. The second thing we're going to do is discuss the why for the Unified MPLS architecture. So we have this architecture that I'm showing you right now with there's a lot of bells and whistles going on there. So what's the motivation for deploying Unified MPLS as opposed to what we might be used to, which is what I'm going to affectionately call traditional MPLS. And understanding the why is going to be crucial for your further understanding of Unified MPLS. The third thing that we're going to do, and the last thing and the longest thing that we're going to do in this video is we're going to touch on the actual components of the architecture in a quick overview, though because this is a larger architecture, we will be taking a little more look into the details there. So we'll get into the details of the components in this video, but also in later videos of the series when we actually get to configuration and the validation portions, just so you have something more practical to ground it to. But for now, we're going to go ahead and just take a look at, in a general sense, how this architecture comes together and how these components contribute to the actual forwarding path. Also, just to note one very quick thing, we're using L3 VPN as an application here, not because this is the only type of service or application that you could run on Unified MPLS, since the configuration of Unified MPLS really only impacts the MPLS core functionality, but rather because this is a series designed to help you learn about Unified MPLS and not about MPLS services. And I figure that since L3 VPN is one of the most popular types of services that people would know how to run over MPLS, I figure it'd be a good inclusion, just so we're not adding like L2 VPN or a bunch of these other crazy MPLS capable services into the fray here for these demonstrations and discussions. One last thing. If you haven't already, please consider looking at the last video in the series. I'll include a link in the description below to it if you need a quick refresher on traditional MPLS. A lot of parallels will be drawn in this video to some of the constructs that we have when we're configuring traditional MPLS. So again, if you need to check out that video, it's the last video I did in this series. It's considering traditional MPLS and LGVPN architecture. Just go ahead and check for the link to it in the description below. So like I mentioned when I outlined what we were going to do in this video, the first thing that we're going to go ahead and touch on is some of the hallmark features in this architecture. So as you can see, one of the most defining features for Unified MPLS when we're comparing it to traditional MPLS is that instead of just having one IHV domain that spans throughout the entire length of the LSP, we've got multiple IGP domains here. So in this case, we've got three IGP domains. We've got one here, and the other here, right? So we've got the three IGP domains here, right? And in this particular demonstration, we have three. The reality is that for your particular scenario, the number is going to depend because you have different requirements and you have different constraints. So how many IGP domains for you will specifically depend on your scenario, on your environment, but for this demonstration, I'm going to use 3. So we'll get into why we actually split up these IGP domains later. We'll get into some of the motivations behind Unified MPLS, but I'll save that discussion for that section. So something else that I wanted to point out, and I'll point out a different color here, something else I wanted to point out was that we have a new router role, right? So previously in the traditional MPLS architecture, we didn't really see these autonomous system boundary routers here, these ASBRs. I'm going to actually go ahead and erase these circles here so I can highlight these more effectively. All right, so we have these 2 ASBRs here. So you didn't really see ASBRs in traditional MPLS because the idea is that in traditional MPLS, we have one domain, right? We've got, maybe an LSPF domain or an ISIS domain that stretches out throughout the entirety of the LSP. And so as a result, you didn't have multiple ASs that you needed to facilitate transit through. Well, now you do because you've got, in this case, 3, right? The point of Unified MPLS, one of the hallmark features, again, is that we split up these domains. And so as a result of that, we have ASBRs here because we need to actually facilitate the transport between the IGP domains here. So the last thing that I wanted to point out here was that if you look at the visualization of the label stack that I've included down here at certain points in the topology, we have the inclusion of a new label here. So this is got to be this blue label. So in traditional MPLS, we've got, with L3 VPN at least, we've got 2 labels. We've got the VPN label, which is exchanged between PEs using VPN v4, and we've got a IHUS LDP label, which is going to point it from PE to PE, right? And that's going to get swapped and all within the actual IGP domain because each is going to have their own label bindings for LDP. So now we've got an inclusion of a new label in that label stack. It slots in right in the middle of the VPN label and the IGP plus LDP LSP transport label there, and it's going to be called the BGP service label. So it's exchanged between the ASBRs. So this blue label here is going to be exchanged between the ASBRs, and we'll cover how this is done later. But it's going to be exchanged between the ASBRs with an extension to BGP called RFC 3107, which is the RFC is titled Carrying Label Information in BGP4. So if you want to read up on the RFC, you can either Google it or I will include a link to the RFC documentation in the description below. But what RFC 3107 does is it introduces a new address family to BGP called the label unicast. It's actually a subsequent address family identifier in a SAFI. So what a SAFI is essentially is that you have your main address family, you have your IPv4, and then you have subsequent address families. You have unicast, and in this case, you have labeled unicast. And the difference there is that the update at RI format is changed in order to include a new field in order to contain an MPLS label. So the label as exchanged between the ASBRs here is going to be crucial because this BGPLU label is one of the major keys that the ASBRs use in order to facilitate their crucial role of bridging the different IGP domains here. Now we've highlighted some of the core pieces of Unified MPLS and the architecture there. Let's talk about some of the motivations, because there's no use learning about a feature if you don't have something to mentally ground it to that you already understand. So for learning to be practical, you need to see the use of something new that you're learning. So it'd be entirely reasonable if you're asking yourself at this point, well, why are we adding this complexity? Why not just keep it to one I2 domain? So why do we need to add all these new components in order to facilitate the unified MPLS architecture when the traditional MPLS architecture worked just fine? And so again, you'd be reasonable to ask that, and the answer that I'm going to give you is immense scalability. So let's go ahead and do a quick review of IGP, shall we? So I've brought up a little blank chalkboard here that I'm going to go ahead and draw in order to demonstrate this. So if you're already familiar with the basic concepts of IGP path recomputation, and you want to go ahead and skip on this section because you're already familiar enough with OSPF and ISIS to get through this, I will include timestamps right about now in the video so that you can go ahead and skip through to the other section if you just want to get through. But for those of you who would benefit from an IGP review, here we go. So with two of the most common IHPs you're going to find in a service provider's core environment, which are OSPF and ISIS, there's link state functionality in each of them that's based on this algorithmic scheme called the SPF algorithm that's expanded to be the shortest path first algorithm. You may also hear this interchangeably called Dijkstra's algorithm. If you've studied these protocols at all, these routing protocols, you'll know that the point of the shortest path first algorithm in the context of these routing protocols is going to be path computation. So with SPF, you're trying to find the shortest path between any two nodes in the network and then map out a tree based on all of the information provided by the nodes in the topology so that you can perform optimal routing between networks in the overall domain given that tree. So SPF compiles all this information that's found in the link state database, LSDB, in LSPF. There is an equivalent database in ISIS called the LSPDB, but essentially it's the same concept. That database is used and the information is pulled from it in order to have SPF compute a tree for that particular area, and then it uses that in order to compute shortest paths. Well, that's great, but one of the really big drawbacks of SPF is how computationally intensive it can become. So if you've got a couple routers, it's probably fine, but if you start to scale your IHP outwards by adding more routers, as you might be doing if, say, your entire company's mission and bottom line as a service provider is to provide transit services to customers, you can run into issues with scalability because SPF starts to become this incredibly heavy process in terms of resources. And the reason for this is that every time there is a change in the topology, so let's say a prefix in a router LSA is removed, and a new router LSA with an updated sequence number and those changes committed to it has to be sent out by that router, SPF has to effectively recompute that entire tree. So every router in that area now must participate in that recomputation, which takes resources away that can be used for services running on your routers, like IPsec VPNs and the encryption of traffic of IPsec, like network address translation in order to perform your address translation. And like, oh, I don't know, the actual forwarding of traffic that your router is there to do in the first place. And so taking away resources from those critical services that have a direct impact on forwarding is probably not the best thing you could be doing for yourself. Now, the reason that every single router has to participate in this recomputation is because the change in the topology that we're talking about and the one that's in question could mean that a path is down that was previously considered to be the shortest path, or that a new shorter path than the one that's already computed and the one that's already selected exists. And SPF needs to recalculate to see whether it needs to make any changes to the path that's selected or not. So let's go ahead and draw this out, shall we? So just to draw everything that I talked about right there in that little segment, that little blurb, we're going to go ahead and draw a topology of, let's go ahead and say, 4 routers. So R1, R2, R3, and R4. So this is going to be the topology for now, and I'm going to go ahead and change it as need be. I'll go ahead and change the color here. I'll go ahead and change the topology as need be in order to demonstrate what I want to demonstrate here. So we've got OSPF1, and we've got area 0. So here's, you can see you've got this IHP domain here, and the idea is that, and we're also going to go ahead and add loopback interface. Whoops, forgot to do that. Pretend that these are all 32 length prefixes because I can't be asked to draw out the prefix length there, quite frankly. 4.4.4.4. Okay, so these are loopback interfaces. They got 32-bit prefix lengths. And these yellow circles are going to go ahead and indicate for us what OSPF interfaces are OSPF enabled. Hint, all of them. Yep, all of them. Okay, so all of these interfaces are going to be OSPF enabled. And the idea is that this is all in one area. So the idea for topological awareness and consistency here is that all of these routers are going to be aware of the router LSAs for all of the other routers because it's in one area. And the LSDB that's constrained to a single area must be consistent within the area by standard. So every single router LSA here is going to contain all of the CF-enabled interfaces and segments. So as you can see here, router 1's router LSA would contain the network for this link and this link, because those are its two CF-enabled interfaces. Router 2's router LSA would contain these three networks right here, entries for those, and so on and so forth. You can see how the principle would apply going down. Now, this works when the topology is fully converged, right? We've got these four routers here. These routers are going to converge very quickly because there's not that much going on in this area, and SPF is a really good algorithm. So it's going to converge pretty quickly. They're going to learn each other's routes and all of that, and the networks that are SPF enabled and advertised and all of that fun stuff, right? So this is where it's fine. Now, imagine if, let's say, some guy comes along and was experimenting on your router and figured out that one of the ways to bring out a loopback interface is to go on the interface and do a shutdown. So this loopback interface goes down from Jimmy's experimentation or whatever, and so as a result, R4 is going to send out a new router LSA because it looks at the link that just went down and went, oh crap, this link that just went down is being advertised by LSPF. Well, I don't have this link active anymore, so I need to go ahead and tell all these other routers, hey, don't send traffic here because you're not going to be able to get the 4444 from me. I have no way to get to it. So as a result, when R4 sends this new router LSA out, what it's going to do is it's going to update the sequence number, it's going to bump it, and then it's just going to go ahead and include this interface here and not this interface. So as a result, that new router LSA from router 4, that new LSA type 1, gets flooded throughout the entire area, and then when router 1, 2, and 3 receive it, they're going to see that something's changed. They're going to see that 4444 has changed, and it's no longer there compared to the old LSA that it had. And so what's going to happen is that old LSA gets bumped, but because the LSDB for the area changed, that area is now a candidate for recomputation on the local routers. So the decision to perform recomputation is handled on the local routers because basically the candidacy for and the criteria for it is going to be, okay, well, is there a change in applicable portions in my LSDB? Yes, then perform recomputation. That's that local router's decision to make, and the decision happens whenever it gets to receiving and processing that router LSA. So it's nothing like a coordinated action. It's the SPF recomputation and the tree maintenance are all centralized on that router's control plane. So as you can see here, because 4 went down, 4's loopback rather, these routers are going to say, okay, well, there's a change now. We have to perform SPF recomputation. And I know my handwriting is just absolutely immaculate and beautiful, right? So it's going to perform SPF recomputation. It's going to figure out, okay, well, 4444 no longer exists in this particular topology, in this particular tree. Let's go ahead and just remove it from the routing table. And let's go ahead and remove it from whatever CEF tables and fibs that we have to, right? So you can see here that works, right? So SPF has performed recomputation and it has removed that link. You think, oh, good, right? Now let's go ahead and say that we add a new link from router 1 to router 3. And we make it such that that link is LSPF enabled. What's going to happen? Well, router 1 and router 3 are going to send out new router LSAs. Because let's think about this, right? Router 1 and router 3 both have a change to make because both of them have a new segment activated. Both of them have new interfaces to add to the router LSAs. So it's no longer just one router LSA that gets sent out. It's two router LSAs that get sent out because router 1 has a change and router 3 has a change. So basically, router 1 is going to go ahead and send out its router LSA, and it's going to say this is LSPF enabled. Now you've got two recomputations that are happening because you have two LSAs that are going to be changing. You've got router 1's that's changing and router 3 that's changing. So when router 1 sends out its, router LSA that's updated with this new interface being added, new network being added, router 2, router 3, and router 4 gotta see it and went and go, oh, well, something has happened. I don't know what it is yet, but in order to figure out whether A, it affects me, and B, whether if it does affect me, then what exactly does it affect me in regards to, and what do I need to change in terms of my view of the topology? It needs to tear out the old tree, perform the SPF recomputation, and include the new changed R1 router LSA along with it. The same thing happens when router 3 advertises its updated router LSA and forces an area recomputation. So you can see here, even with 4 routers, just by performing 2 changes, we've had 3 recomputations now. Now, think about in a service fire, you don't just have 4 routers, right? If you're in a serious service fire, you've got, thousands of routers. And imagine if you were to pack them all in one area, that would be a catastrophe because you'd have SPF recomputation events going off every single other second. Because when you're adding routers out and you're expanding the area outwards, you're actually doing 2 things that we're really thinking about it. The first thing, as it relates to recomputation, the first thing is that you're increasing the frequency of recomputation. So with 4 routers and just a couple of interfaces, there's just a few things that could fail relatively, right? In order to cause an SPF computation, there's a relatively few amount of things that could possibly change. As you expand your area outwards, as you add more and more routers, the possibility and the statistical probability that you're going to experience SPF recomputation at a given moment of time increases with the amount of routers that you're adding and the amount of elements that you're adding, because now there's a greater amount of things that could change, that could fail, that could, be modified in order to cause an SPF recomputation. The second thing you're doing is you're increasing the severity of SPF recomputation events when it happens. So you're already increasing frequency, but now you're increasing the severity of these recomputation events because now more routers have to stop what they're doing and say, oh, shoot, something happened. Let's go over here and perform SPF recomputation. Oh, something else happened. Let's go over here and perform SPF recomputation again. Oh, something else happened. This pattern starts to continue as you add more. And not only that, but again, you've got more routers that are doing recomputation. These particular trees are rooted at the router because every single router has a different position in the topology. So, router 1 is in a different position than router 4 is because router 1 is connected to router 2. And if it wants, and it's also connected to router 3 because of this new link that we've added, right? So it's connected from router 1 to router 2 and router 1 to router 3. Router 4 is just connected to router 3, right? So if you were to draw this out, if you were to map all of this out as I have here, router 1 and router 4 are clearly in different positions. So the tree that could work for router 1 to map out its shortest path to things won't necessarily work for router 4. So as a result, SPF will locally compute these trees. And if you have more and more routers in a single area, that means that the severity increases in terms of your recomputation events because each router has to recompute its own local tree. And for a majority of those routers, things might not even have changed, right? Because in order to know whether things have changed as a result of this new change that happened to the topology and whether that change affects it, it needs to perform recomputation. Well, if it performs recomputation and it figures out, oh, nothing's changed, I'm good to go, that just affects someone else in this topology, then you've just wasted that router's resources that could have been used and allocated somewhere else. Now, what you might be saying is that you've studied OSPF and ISIS for a little while, and you know that OSPF has this feature called areas in order to help you segment off the IGP domain in order to prevent that exact issue. And ISIS has areas as well as including levels in order to help you abstract the backbone and everything, right? So you know that these constructs of areas and levels in these IGPs are designed to help increase the scalability by, in part, reducing the impact that SPF recomputation has on the network. Because, for example, in OSPF, this SPF recomputation event is just significant to the area, right? So this event right here is locally significant to the area because each area has its own SPF tree. And so that's part of the appeal of areas for scalability is that this SPF recomputation process, the only way that it can get triggered is if a change happens within that area for like a type 1 or a type 2 LSA, and the recomputation would only happen for routers within that area. So it reduces the likelihoods and by reducing the number of events that could cause it, and then it reduces the scope of an SPF for computation if and when it does happen. So shouldn't this help with scalability? And the answer is that you're absolutely correct that this helps with scalability. The concern is, however, that it might not be enough to help with scalability. If you think about a service provider core, you have thousands of routers, and in that case, areas might still present architectural and scalability challenges. As well as that, areas can become super hard to manage and design properly, particularly something like OSPF, because if you think about OSPF, you've got a logical hub and spoke, right? You have this backbone area 0, and then all of your subordinate areas here have to hook into it. And if you don't, right, if you have this scenario, then you need to essentially tunnel your traffic essentially through area 4 up to area 0 using something called a virtual link. You could also do it with a GRE tunnel, but that's the preceding method to doing OSPF virtual links. So the point is that you have this virtual links to go between them if you don't have areas that directly connect into area 0. But this whole area 0 construct is what makes it hard to design. Sure, it's scalable. Sure, these areas are segmented from each other from a topology perspective and from an SPF recomputation, SPF tree perspective. But you still have this logical hub and spoke because you have this one giant area 0 block at the top, and then you've got subordinate areas that need to connect up to it if you don't want that area to be completely isolated within topology. So while you're absolutely correct that areas and levels can help with scalability, it adds complexity to multi-area designs because every area, again, by standard, has to go back to a backbone in some way, whether it's a connection to an ABR or via a virtual link to an ABR that can tunnel that area back into the backbone. And ISIS, it's more flexible than this because all of your backbone routing is being abstracted into this level 2 routing level, but you still have a concern of design complexity when you add in more areas and stuff like that. Furthermore, within an IGP domain, you still need to have inter-area routing. So if you're an IGP domain, for example, OSPF has the concept of a type 3 LSA, your summary LSA. And in ISIS, you have the concept of, okay, well, the routes that you learn from level 1 as a level 1-2 router get copied into this level 2 LSP that goes throughout the backbone, right? So either way, somehow, shape, or form, you're still facilitating inter-area connectivity, and that means that you're still going to be presented with some potential scalability challenges because within the domain, you still need to route between areas. Again, there are features like stub areas and all of that that will help you in order to reduce that footprint, but you're still then layering on complexity by using more and more features in the IGPs that are designed to help with scalability. So, with this issue that's being presented, what's the solution? Well, with Unified MPLS, the solution that's actually being presented here is that instead of using areas, instead of using levels and relying on them solely, we could still use those concepts, by the way. These are still separate IGP domains, but going straight into it, that's a good segue. Unified MPLS proposes a solution that says instead of relying solely on levels and areas in order to segment the IGP and add scalability that way, what if we just take the elementary approach and split up the domains altogether? If the problem is that we are scaling our domains too far out, what if we just split that domain up in order to make that individual domain more manageable? Make it so that these domains, from the perspective of the IGP, are entirely separate. Well, that's what Unified MPLS seeks to do. Hence why you see these separate IGP domains, and that's the motivation for it. Scalability. By separating IGP domains, you add immense scale because you can just add new IGP domains should scalability start to become a pressing issue. And the design for that IGP domain, assuming that it's mostly consistent with the other IGP domains, would be linear with the other IGP domains as you grow out in terms of difficulty from a management perspective, as opposed to an absolute mess that you can get into with OCF areas and the multi-area design there, and the similar mess that you can get into when you start to scale ISIS out. So, in summary, one of Unified MPLS's key advantages is the immense scalability that it provides, and in a relative sense, the manageability that scalability comes with. And that's one of the reasons that you'd be deploying Unified MPLS. So if you'd like to read into some of the other benefits and use cases from a design perspective, I will include links in the description below to Unified MPLS white papers and presentations from the likes of Cisco and stuff in order to allow you to read up on those so that you can learn more about the Unified MPLS technology and the architecture and use cases and all that. So if you want to, be sure to check those out. Again, there are links in the description below if you're interested. So in this video, we covered the hallmark features of the Unified MPLS architecture, as well as one of the motivations behind using Unified MPLS, which was the scalability that you get. And I covered the scalability implications that you might have that would convince you to go over to Unified MPLS. So in the next video, in the next part, this is going to be part 1, next is going to be part 2, we're going to go ahead and talk about the actual components of the architecture. We're going to get a little deeper into that, and then we're going to go ahead and look at, in that same part, how these components come together in a more general big picture sense in order to bring the Unified MPLS architecture together and get it to actually form an end-to-end forwarding path. So after that, we're going to go ahead and get into the practical demonstrations and configurations of the various Unified MPLS components and to actually get architecture working in a lab. So if you enjoyed this video, go ahead and leave a like down below. If you have any comments, suggestions, feedback, or just want to say hi, more Cisco, I don't care, go ahead and drop a comment down below. I love hearing from you guys. I love talking to you guys there. So again, go ahead and leave a comment down below if you'd like. And go ahead and, if you haven't already, subscribe and turn on notifications and all that so you don't miss any of my new videos coming out. And with that, I hope to see you guys in the next part. And with that, more Cisco. See you guys there.